um, the video for homework 1, module 5, equilibrium and acid reactions. Homework 1 is on static and dynamic equilibrium. This is for year 12 chemistry. Okay, so for the multiple choice, first question is an answer sample question. That is the particle, okay, I'm gonna call this gray. Particle gray reacts with particle black to form this molecule of gray and black. The system comes to an equilibrium. Diagram shows this as initial reactants. So it starts from everything in separate form, okay? So the choice will be A, right? It's asked me to choose a correct answer, which shows dynamic and static equilibrium accurately. So it will be A. The reason being that dynamic equilibrium here is by definition, you have like forward and reverse reaction happening at the same rate. It must be A because like you have like forward reaction. That means that you go from the separated atoms into the combined atoms, and you could also like go from the combined atom into the separated atoms. Whereas say B, it doesn't go in the forward direction because there's no like black uh by itself atom that can be combined with like these gray atoms, and C just can combine them, but there's no like combined being split apart, so it can't like be reversible. Same thing with the D. Okay, so like A is the correct answer for dynamic equilibrium, and this was of course static equilibrium because this equilibrium can only be formed uh, like because like the combined molecules are allowed to be splitted, but then you can't get any more bind to the combined molecule. So it's only like one-way reaction. That's why it's static equilibrium. Question 2 is a sample question again. So it says, in which diagram is the system most likely to have reached dynamic equilibrium? Uh, of course, it should be either B or D because we know that dynamic equilibrium can only exist in closed systems, so you must have a lid on, especially with reactions that has like a gas produced while it's being mixed in terms of solids or liquids. Okay, this one would be D because D shows that there's like carbon dioxide in the air around it, whereas B choice doesn't, like it only has this calcium carbonate. Okay, question 3. Which of the following are equal for chemical system at equilibrium? By definition, will be the rate for forward and reverse reactions. Okay, it's not necessarily the concentration. Okay, concentration don't necessarily are equal in the dynamic equilibrium, but rates are. All right. Question 4. A chemical equilibrium may be established by starting the reaction with any quantity of reactants and products. Okay. Um, yeah, you don't have to restrict that. You can start with a mixture of reactants and products. You can start with just reactant, it doesn't really matter. Doesn't as long as you reach dynamic equilibrium with equal rates for both forward and reverse. Okay, a bit noisy around me. Okay, anyways, question 5. Which of the following is not a correct difference between static and dynamic equilibrium? Um, so A says dynamic equilibrium, the reaction will be reversible and the final state will not be completely composed of the products. Um, this is accurate. This is correct, right? So in order to be reversible, you must have products and reactants simultaneously together. Okay. Question 6. Yeah, sorry, I'm just being interrupted. So, and B choice is like in static equilibrium, the reaction may be reversible, but the reverse reaction rate is 0. This is true, so it's correct. That's by definition. Okay. In static equilibrium, the molecules remain relatively stationary in solution. Yeah, this is true, right? Because nothing's doing anything, so relatively stationary. D is incorrect in the sense that it says in dynamic equilibrium, the percentage composition of reactants will remain equal. This is not necessarily true. Okay, in fact, this is never true, and then never like exactly the same amount. Okay, that'll be like very, very lucky. Okay, so equilibrium, dynamic equilibrium doesn't restrict like the how much is your concentration. It only restricts you about rate. Okay. All right, question 6. Which of the following setups would be best modeled as a closed system? Uh, so a beaker containing standard solution is not closed because, like, I mean, it's stuff can vaporize and stuff. A conical flask placed underneath a burette. The same thing, conical flask is open, like lid. The burette containing, again, burette is also opened. Okay, a volumetric flask containing standard solution capped. Okay, so that the solution can't be mixed. So yeah, this in case will be a closed system. Question 7 says in collision theory, which factor affects the rate of chemical reaction? Um, selection A says that the rate of collision, number of halogen atom. No, that has nothing to do with like rate of reactions. So random. Okay. I'll just put my headphone on. Should be better now. Um, for B says the molecular orientation, rate of collision, activation energy. This is correct, right? This is what we had for definition of collision theory. These are the two topics, the three factors. C again has this electronegativity and heat of entropy. Not really. Okay, these are not factors of collision theory. B is incorrect too. Right, so let's then move on to the extended responses. A of 8A says that to construct an open system with a closed system, you could say that the open system transfers both matter and energy. Okay, whereas closed system only permits energy exchange. This is just like outlining the significant differences. And then I basically start to answering about like whether reversible reaction is happening in which one. Like just give it more like more detail and more like in-depth understanding. Yeah, so reversible system is allowed only in closed system, while open system have like material interaction with surroundings, so never is reversible. Okay, so I think two of like these differences give you those 2 marks. So just like at least convince yourself of those 2 marks, right? Just try to write like two separate things, and it should be fine. So and B says using a specific chemical reaction. This means that you have to write chemical equations, okay? And explain why equilibrium can only exist in closed system. So the thing with why equilibrium can only exist in closed system is that when they ask about equilibrium, static equilibrium is of course an equilibrium, but when they don't say that and they just mention equilibrium, it's by default talking about dynamic equilibrium. Okay, so this question is almost like why dynamic equilibrium can only exist in closed system. Okay, so you can talk about how like open system creates these lose of contact of your reactants or products, so they just goes away. You can't establish any more contact. Therefore, you sort of lose its collision and successful collision doesn't react anymore. So it always goes to static equilibrium. Yeah, sort of mentioned that. So what I said is basically I said uh, an example, I asked for specific chemical reactions. So consider the decomposition of calcium carbonate. This is one we learned in class in stochastic memory. It produces carbon dioxide with solids. So it's a heterogeneous reaction. Yeah, this is just me showing off a little bit of my general knowledge about like, the type of this reaction. Yeah, with extended response, basically try to sound smarter. Like that's a general advice for like how do you ensure you can get all the marks of this question. Uh, the correct answer is nobody can ensure that you can get all the marks. It's just like do the best. Depending on the marker, you maybe have a higher chance to get a higher mark. So yeah, so this is the reaction goes as this. It's heterogeneous because you form solids and gas in these in different states. And I talked about that in open system, carbon dioxide easily escapes and then reacts with uh, calcium oxide again. So meaning that it cannot be reversible. It's just never compacts. Okay, it fails to establish dynamic equilibrium. Whereas in contrast, a closed system ensures that carbon dioxide is always in contact. Yeah, there should be is. Typo here. It doesn't change a lot. It's always in contact with calcium oxide, so reaction is allowed to be reversible. Thus, dynamic equilibrium is only allowed for closed system. Moving on, C says that describe a key difference between static and dynamic equilibrium. Provide an example of each of equilibrium to aid your answer. So static equilibrium, so this question, I basically structured my answer as in like answering as a dot point, which it was pretty obvious because the question asked about dynamic and static. So it would be very nice to split into two dot points, each explaining static and dynamic separately. This way you can structure both like different aspects in like a sort of similar format. So it makes it very easy to find out differences and similarities. Okay. This is like a much better way to write out this response. So for static equilibrium, I wrote that it describes a state. So I define it first. So I always start with the definition. No exclusion. Everything starts with definition. So static equilibrium describes a state where forward and reverse goes to zero. This is that. So that no macro or microscopic change. Such a reaction is best modeled with a combustion reaction. This is my example. Okay? And I'll sort of also explain why this is static equilibrium by talking a little bit about Gibbs free energy, small reference, explaining more. And dynamic equilibrium, you can see how those two dot points are basically the same structure. I start talking about the definition. They have equal but not zero rates. So see, I have this equation, this equation. That's very obvious. This is the difference. Okay. So despite no macroscopic change, right? So this is both micro and macro are like no change, but this is despite no macroscopic change, it's still microscopic influx between reactants and product. So such a reaction can only happen in a closed system, and static equilibrium can be both. Okay, just highlighting some similarity and differences. And kind of an example as well here. Okay, so this is how I structure this action. Yeah, basically. Right, then have a look at question 9. So question A says that explain 3 factors that affect chemical reaction in collision theory. Uh, so for this question, my tactic is like started with a definition. Okay, what is collision theory? And next section like splitting into 3 dot points, each talking about one factor. Right, with collision theory, you talk about factors such as number of collision, activation energy, orientations. Okay. People like to go towards saying concentration, pressure, and temperature. Uh, yes, but no, because it's collision theory, right? We should stick to the definition of collision theory, which is revolving around these 3 factors. Okay, so don't forget the year 11 knowledge. So for number of collision, this is basically the mole of concentration of chemicals. Yeah, the larger the collision number, the faster the rate. Just demonstrate your understanding. Okay. And activation energy as well. Define it. So the minimum energy required to collide successfully. So this is affected by temperature of the reaction, and larger temperature means that more particles can engage in a successful collision, leading to faster rate. Orientation is that the orientation of the reactants also contributes to the likelihood of a successful collision. The exact molecular orientation depends on the reaction. Okay. Question B, outline 2 limitations of the collision theory in explaining the rate of chemical reaction. Yeah, this question is hard, right? You can't really think about any limitation because it's a pretty accurate theory to be honest. But if you think critically, there should be like points that you can point out. First of all, is the collision theory only accurately describes gas or liquid molecules due to uh, their significant motion, right? Like we talk about solids, it doesn't really do as much. I mean, like if I increase the number of like moles of solid, it doesn't increase the reaction rate that much, right? It's like moderate. But the second one, there's that the collision theory does not consider the exact mechanism. Yeah, that's true. Because like you just say colliding, particles collide, but that's not really what happens. What happens is really interaction of like forces between atoms, and breaking of bonds. So chemical mechanism was like very much lack of detail in collision theory. So that's the limitation for that about. Okay. All right. Move on. Question 10. Question 10 says that the reaction between hydrogen gas and iodine gas forms hydrogen iodide, which is also a gas at room temperature. So the reaction forms an equilibrium mixture in a closed container. Question A says to write a balanced equation for this reaction. Common question style in HSC is like they give you this information and ask you about the chemical reaction in the first step. So that's what we do. And question B, explain why an equilibrium cannot be formed when the container is open. This is because everything in this reaction is a gas, okay? So gas particles might escape and lose contact with each other, meaning that we can no longer react in either ways, okay? Some grammatical errors, like we can never react. Thus becoming irreversible. Open system basically means everything irreversible, and you don't get anything further from that type of thing. Okay. Part C. So the following graph shows the change in concentration of three gases as the reaction proceeds with time. Explain what happens at the time labeled as T0, and explain why concentration of gases remain unchanged after this time. So at T0, we can see how the concentration stops changing for all of the three gases. This is by definition a dynamic equilibrium, right? So the reaction has established a dynamic equilibrium, and the dynamic equilibrium system has both forward and reverse rate equals to zero. Thus, there's no going to be macroscopic change in concentration. Yeah. Question 11. It says soft drinks. They are described as carbonated because they contain dissolved carbon dioxide, which forms the following equilibria. Okay, so it's carbon dioxide aqueous dissolved into carbon dioxide gas. Now, if the can is left open, basically what happens is like this gas just escapes, and then like this is converts to more gas, and this gas just keeps escaping, and eventually all of the CO2 dissolved is gone. Okay, they reach some sort of dynamic equilibrium. This is when it tastes flat, okay, and appears not fizzy. Okay, so let's use collision theory to describe it. So when a can is opened, the gaseous carbon dioxide is allowed to escape the can. As it escapes, the concentration of carbon dioxide gas will decrease. So the number of collision between carbon dioxide gas will also decrease. And this goes the same with the number of successful collision, and the reverse rate also decreases as well. Therefore, overall, the reaction favors the forward direction. It just keeps going, while the gas is continuously losing its quantity. So yeah, eventually just never reversible. So static equilibrium is established when everything just flows off. Okay, so life tastes flat. Okay. Right. I mean, students can always pause the video just to copy the answer or something. And remember that you have to fix all the mistakes. Question 12. Using concepts of enthalpy and entropy, explain why a combustion reaction is irreversible even in closed systems. Well, this question you have to talk about the Gibbs free energy and basically the two drives of reaction. Combustion reaction, first of all, they're extremely exothermic, meaning that delta H is very, very negative. And they also produce a lot of like entropy as well, because like produce a lot of particles that's increasing more energy distributed ways. It's introducing chaos, right? So together, the skip free energy delta G by definition delta H minus T delta S, write this equation, very important. Gives you a very negative delta G, so by definition that's so like spontaneous, it never goes back. So it's not a reversible reaction, spontaneous forward. That's why it's never like, dynamic equilibrium. Okay. Question 13 is a classical talking about model question. Okay, they give you like this model already given to you. Other questions will be like ask you about the model, so you have to describe the model yourself. These type of questions are more, I would say, more difficult. But then this one already have a model for you. You just need to allocate the aspect of this model with the chemical idea. So question said, be very careful about the wording, right? It says assess the usefulness of this model in demonstrating concept of dynamic equilibrium. So we have to really assess the usefulness, okay? So my logic here is to talk about pros and cons in two dot points, okay? Talk about good things, talk about bad things, so that I'm really assessing everything, yeah? So pros are, you can say that the aspect of the model is directly linked to the aspect of the system, right? That's why it's good. And then you have to be very specific about these aspects. So follow on, I say, for example, the flow rate into the container, it sort of represents the flow rate. This is me making direct link between the model and the chemical like aspects of chemistry. Okay. This is how you answer these questions. For every model, you have to make links between like aspects of this model. How is it representing the chemical ideas in order to assess the usefulness? Okay. Yeah, so and then the water flowing out is kind of like the reverse reaction rate, while the water level inside the container is like the concentration of the reagents. Okay. Yeah, so like, as in like the system modeling dynamic equilibrium is very accurate because the water level doesn't change, meaning that it's at dynamic equilibrium. Okay. So yeah, so like so the height of the water. So if I start reading here, height of the water can also represent concentration of the product. Yeah. So the water flow rate being equal is an accurate demonstration for the system dynamic equilibrium. So this is like why this model is good. And then I talk about why this model is bad. This one is a little subtle, and then it takes some effort to really like express your point clearly. And the idea is like this model doesn't really show the interaction between the chemistry, right? Look, in dynamic equilibrium in terms of chemical system, molecules are reacting. This does not show that. Like they're exchanging between each other. This does not show that because the water just like flow in and flow out. It does not form a cycle like chemical equilibrium. Chemical equilibrium goes from A to B and then B to A back. Well, this is like A to B and then just gone, right? This is like that, and then just gone, right? And you're not forming a loop. Really to emphasize this is like the point that is not useful in this case. Okay. So the one I said is like I said the model shows a lack of detail on the interaction of the reverse reaction, i.e. the model shows water flowing out, but in real reaction system, chemical do not just flow out. Okay, and then they rather react to become reactants again. So the subtle cycle between reversible reactions was not demonstrated. Okay, yeah, talk about that. All right, shall I move on? Question 14. So this one says a reaction between dinitrogen tetroxide and nitrogen dioxide is a common example of dynamic equilibrium. There it is. So it says some amount of that is injected into a closed vessel. the graph shows the changes in concentration of that and that with time. Using collision theory, explain what's the trend shown in the graph. Yeah, so asking about the trend, you have to talk about every single like significant time interval. That's what we talk about initial, sort of during the change and after like this line here. So 3 dot points, talking about each. Initially, the system only have dinitrogen tetroxide, so the successful collision only happens between dinitrogen tetroxide. Therefore, the reaction just goes forward and produce NO2. So while reaction is happening, right, the concentration of NO2 would keep increasing so that there's going to be more and more collisions happening between like NO2. So more collisions, then therefore more successful collision between NO2 molecules. Simultaneously, NO2 start to react back into N2O4. And as a result, the concentration of reagents stops changing at some point when the rates are equal, right? So the concentration of reactants stop changing. This means that the rates for forward and reverse has balanced out. So i.e. same amount of successful collision between this and that. So in total, your concentration just does not change after establishing equilibrium. Question B says like why? Why does the concentration stop changing? You can just say, as discussed. This is sort of like question A, but like we've discussed. So say that as discussed, concentration is a macroscopic property and a dynamic equilibrium. Macroscopic property just does not change anymore. So the reaction has not stopped after, just to point that out, right? Still reaction happening, just like for the same number of N2O4, it's going to be like same number of NO2 coming back. So they're not changing in a macroscopic scale. So this is due to the fact that between reactant products still exists a continuous flux between NO2 and N2O4. They are still converting back and forth with a sample with the same rate. Okay. Yeah. So this concludes our homework talking video for homework 1, static and dynamic equilibrium in 12 chemistry, module 5. Okay. Any question you can ask in class. My best to answer.